For 5 straight days, one stretch of equatorial ocean kept stepping beyond its own daily temperature record. Each new reading rose above the last, while an exceptional pulse of equatorial wind, among the strongest measured in that region, continued to drive heat into the water behind it. Events of planetary scale are not supposed to look as if they are speeding up while we watch them. Yet on the 11th of June, the United States moved from waiting to warning. The National Oceanic and Atmospheric Administration upgraded its El Niño watch to a full advisory. In ordinary language, the signal had crossed the line. El Niño was no longer something approaching from the future. It had arrived. And what has unsettled researchers is not merely the warmth itself, but the pace at which it appeared, ahead of the very forecasting models designed to anticipate it. That makes the next question feel unusually heavy. If this is the opening act, what might the peak become? For calm space, this is the kind of slow-building planetary story that may unfold for months, and it asks us to look carefully before the headlines catch up. The first clue is a number that refused to stay still for 5 days. Far from any familiar shoreline, along the equator in the central Pacific, a region of ocean has been behaving in a way that made climate scientists pause. A temperature record was set, which by itself no longer shocks quite the way it once might. But then the following day exceeded it. The day after that did the same. Again and again, for 5 consecutive days, the central equatorial Pacific broke the record for that date. Each time, edging higher rather than easing back. At the same time, an unusually powerful wind burst along the equator, kept feeding additional warmth into those waters, as though the atmosphere were giving momentum to an ocean already moving too quickly. The image is quiet, almost invisible from the surface, but its meaning may be anything but small. Normally, a phenomenon like this is tracked in patient intervals. Scientists smooth it into 3-month averages, wait for seasonal confirmation, and discuss it through updates that arrive at a measured pace. This time, the daily observations from the middle of the Pacific show a line separating itself from the pack of every recorded year and continuing upward. That is why the 11th of June mattered. NOAA had already been watching the developing signal for weeks, but the advisory changed the status from possibility to present reality. El Niño is here. The words are familiar, perhaps too familiar, softened by years of weather segments and seasonal outlooks. Still, familiarity can be misleading. A known name can hide a very unusual entrance. The unease among specialists does not come from the simple fact that El Niño formed. It comes from the manner of its formation. It appeared early, strengthened quickly, and moved ahead of the models expected to track its rise. To see why that matters, the usual timing has to be remembered. In many years, the ocean hovers near the threshold during spring. Forecasters remain cautious. The signal flickers, and only later, often in late summer or early autumn, does the formal declaration arrive. By then, it is commonly less a surprise than an official confirmation. That rhythm gives the system a certain predictability, or at least the appearance of one. This year disrupted that cadence before the Northern Hemisphere summer had properly settled in across many places. Forecasters, using careful language, have described the event as developing earlier and faster than most events on record. That phrase may sound restrained, but it carries weight. Earlier and faster than most events on record means the ocean atmosphere system is not simply following a familiar script at a familiar tempo. It raises a quieter and more difficult question. Are the signals still giving us the lead time we have come to expect? In a sleep-friendly documentary about space and Earth, this is the kind of detail that deserves to be slowed down rather than rushed past, because the smallest shift in timing can change the way an entire season is understood. The historical comparison sharpens the picture. When scientists examine the modern reanalysis, a continuous reconstruction of ocean temperature extending back to 1940, and place this year's curve beside all the others, this year sits above them. not just among the highest, but above every single year in that dataset for the central equatorial Pacific. The warm line for 2026 rises over more than 8 decades of records, including the major El Niño events remembered from 1997 and 2015. Even more striking, it is doing so in June, well before an El Niño would normally be expected to reach something close to its peak. A graph like that is not dramatic in sound or color, but it may be one of the clearest ways to see why the moment feels so unusual. Put the pieces together, and the outline becomes hard to ignore. There is an ocean region setting daily records. There is an official advisory issued weeks earlier than the usual seasonal rhythm might suggest. There is a temperature curve standing above the modern historical record before the event has matured. Those facts matter, but they may not be the deepest part of the story. They are signs on the surface of something more basic: the rate of change. The speed is what turns an expected El Niño into a sharper question about forecasting, preparedness, and how much warning the planet is still willing to give. In this story, warmth is the visible signal. Speed may be the message beneath it. Precision matters here, because El Niño is not a vague label for unusual weather. At its simplest, it is the warming of surface waters across the central and eastern tropical Pacific, coupled with changes in the winds and storms above that water. Scientists measure the warming against the long-term average for the same place and the same time of year, so that June is compared with June, and one region is compared with its own normal conditions. That method matters because it strips away some of the noise and lets the anomaly stand out. Right now, the anomalies are not faint. In the far eastern Pacific, near the coast of South America, sea surface temperatures are running more than 2 degrees above normal. The number itself is important, but the speed of the climb toward it may be the more unsettling part. In the central Pacific, the area most closely watched for the official index, the water has already crossed the weekly threshold used to define El Niño, and it has not stopped rising. That does not mean every consequence is already known, and it does not allow anyone to predict every flood, heat wave, or storm with certainty. But it does suggest that the system has entered a phase worth watching with care. A warm Pacific is a phenomenon science has studied before. There are charts, analog years, and a forecasting machinery built around previous events. What feels different in this moment is how quickly the signal has strengthened and how early it has done so. If there is one thread to hold on to as the year unfolds, it is this. The warmth is not the only warning. The speed may be the warning. A Pacific Ocean, warming more quickly than the forecasting machinery expected, is not just another uptick on a climate chart. When thresholds fall early and records arrive before the season says they should, the ocean is sending a more unsettling message. It suggests that one of Earth's largest systems is behaving in a way our strongest tools did not fully anticipate. And once that happens, a quieter question begins to matter. If the models missed this part, what other parts of this event might they be understating? It is reasonable to wonder why any of this should feel personal. If you live in Ohio, Texas, or the south of England, the temperature of water near the dateline can sound remote, almost unreal, like a number from a place that belongs only to maps and satellites. But that distance is misleading. The condition of the Pacific acts, with very little exaggeration, like a master control for weather across a vast share of the world, including the country many viewers are watching from. When that control shifts, hurricane seasons can change, drought patterns can shift, food prices can be affected far from the water itself. One region of a continent may face flooding while another faces fire. This is why the signal matters. The dial has moved sharply, early, and faster than expected. Some of the first traces are already visible, if you know how to read them. A marine heat wave has formed as a broad tongue of unusually warm water, reaching from the islands of the South Pacific toward the coast of Southern California, where it connects with the familiar El Niño pattern near Peru. Swells are striking the shores of Hawaii and California. In the eastern Pacific, the hurricane season has already produced named storms with warm water and calmer winds, combining in a way that could help the next storm intensify. And in the Gulf of Mexico, a warm, wet, dangerous setup is developing this very week. We will return to that in detail, because it may be the clearest example of how a record set in the open ocean can become a warning along an American coastline within days. So here is the path ahead, and it is worth laying it out gently before we go deeper. First, we need to strip away the jargon and understand what this event actually is, so that the word strange has a clear baseline behind it. Normal has a shape, and only when we see that shape can we understand how far this pattern has stepped away from it. Then we will look at the measurements themselves, the numbers, the monitoring dials, the probabilities, and the genuinely startling projection now being indicated by one of the world's best models. After that comes the harder question, the one that headlines often avoid. Why did the models undershoot this? And what does it mean when reality begins by outrunning the forecast? Finally, we will bring the chain home, from record-breaking water to your coastline, your summer, your sky, and eventually the weather outside your window. To understand why a 5-day run of records is so unusual, we have to slow down around the word record. We hear it so often now that it can lose its force. But a daily temperature record in a defined ocean region is not the same as one unusually hot afternoon in a town. It means that, for that specific calendar date, that stretch of sea is warmer than it has been across the full period of reliable measurements, decade after decade after decade. One broken record would already matter. 5 in a row means something more dynamic is happening. The ocean is not simply sitting on the warm side, it is moving beyond its own past, day after day, setting a new ceiling and then rising through it almost immediately. A useful image is a runner who does not merely break a world record once. Imagine that runner doing it again the next morning, then again the morning after, for 5 mornings in succession, while a tailwind that is itself exceptional continues to strengthen. That is the kind of pattern the data is sketching. It helps explain why the people who spend their working lives studying these charts stopped treating the development as routine. The phrase now appearing in forecast discussions is off the charts. In this case, it is not just dramatic language. It describes, quite literally, a line rising beyond the normal range used to plot it. It also matters who is using that language. This is not coming mainly from anonymous voices trying to sound alarming online. It is coming from institutions built to be careful. Government forecasters and seasonal modeling centers whose work is tied to official advisories and later judged against reality. These are organizations trained to hedge, qualify, and avoid exaggeration. When that kind of institution upgrades a watch to an advisory weeks early and begins discussing consecutive broken records, we are not simply watching hype gather momentum. We may be watching cautious people reach the edge of cautious vocabulary. That difference is important. Caution is part of their job, and in many ways, it is the reason their warnings carry weight. When forecasters with a professional resistance to drama begin to sound concerned, the signal deserves attention. It does not mean every possible consequence is certain, and it does not remove uncertainty from the forecast. But it does suggest that something in the system has crossed into territory that even experienced observers are treating with unusual seriousness. Now place that speed beside one more contrast. Less than a year ago, this same Pacific was not in a warm phase. It was on the cooler side, carrying the faint signature of the opposite pattern, the cold one, associated with a year that often pushes conditions in the reverse direction from what we are about to describe. The planet's largest climate seesaw was tilted the other way. Then, over the span of a single school year, it moved off the cool side, passed through the neutral middle, crossed into warm territory, and kept rising until it had broken records for 5 consecutive days and forced an early advisory. That is not the slow, barely visible creep many people imagine when they think about climate. It is a rapid swing of one of the largest levers in the system, moving from one side toward the other in months. The ocean did not ease gently over the line, it lunged across it. And that suddenness is part of what makes the present moment so difficult to dismiss, because speed changes the way risk feels. It raises the possibility that the coming months may not behave neatly within the boundaries that forecasts first suggested. Before we go further though, there is one central fact to keep in mind. An El Niño that is breaking records this early and running this far ahead of the models has not yet reached the part of the year when these events usually peak. The peak does not arrive in June. It comes later, in late autumn and winter, still months away. So the records, the lines rising above 1,940, and the startled tone from forecasters are not the ending of the story. They are the opening movement. And if the opening is already this loud, the question becomes what the climax may still have left to show us. Stay for a moment with the question researchers may be asking in quieter tones. If the opening phase already looks unusually intense, and if the schedule itself seems to have moved ahead, then what kind of season is this system preparing to deliver? To make sense of that unease, we have to return to the ocean, not as a flat blue surface, but as a moving machine with wind, heat, and rainfall all tied together. This is the essential starting point. What El Niño actually is, and why the word early carries so much weight. Imagine the equatorial Pacific, the broadest continuous sweep of water on Earth, stretching so far that it reaches across nearly half the planet. In ordinary conditions, trade winds blow persistently from east to west, pushing from the coast of South America toward Indonesia and Australia. They are not occasional breezes. They are a steady, year-round force, and given enough time, they herd the warm tropical surface water westward, stacking it on the far side of the basin, as if the ocean were tilted like a bathtub. Near Indonesia, that warm pool becomes deep and heavy. Farther east, close to South America, the displaced surface water is replaced by cold water rising from below. That normal arrangement may sound simple, but it sets the pattern for an immense atmospheric engine. In the Western Pacific, where heat gathers, air climbs, storms build, and rain falls in vast tropical bursts. In the Eastern Pacific, where cooler water dominates, sinking air helps keep skies clearer, and the coast of Peru remains among the driest regions on Earth. Wind, water, clouds, and rainfall hold each other in place year after year, like parts of a quiet mechanism turning in balance. Scientists have technical language for this balanced seesaw, but the picture matters more than the label. Warmth and storms to the west, cooler water and clearer skies to the east, all restrained by the winds. El Niño begins when that engine falters, and in a sense, starts to reverse. The trade winds lose strength. At times, they do not merely fade. A burst of wind pushes from west to east, known as a westerly wind burst. It is as though a hand has entered that tilted bathtub and shoved the stored warm water back across the basin. Once that shove begins, the warm pool that usually remains in the west starts sliding eastward along the equator. It spreads into the central Pacific and can eventually reach the coast of the Americas. The cold upwelling near South America becomes covered by a layer of warm water, and because warmth and tropical storms tend to move together, rainfall that would normally concentrate near Indonesia begins forming farther out over the open ocean. The broader tropical circulation shifts with it, and that displacement can touch jet streams and storm tracks across the hemisphere. This is why El Niño should not be imagined as a single storm or a brief weather episode. It is the planet's largest natural year-to-year climate swing, and it is underway now. One detail deepens the concern. The wind burst that can help trigger this change is not limited to the surface. When warm water is driven east, it does not simply smear across the visible top of the sea. It also launches a slow-moving pulse beneath the equator. A buried surge of warm water known as a downwelling Kelvin wave. From a boat, it would be invisible. From a satellite, it would be difficult to read directly. Yet beneath the surface, it functions like the heavy transport system of the event, carrying heat eastward until, weeks later, that stored warmth can emerge and strengthen the surface, warming that instruments record. This hidden movement matters because it tells us the ocean has not only changed at the skin. Heat is being transferred through the body of the Pacific, and this year, forecasters are uneasy because the wind burst that helped force the event was, by their own measurements, locally one of the strongest on record. The initial push was unusually powerful. The subsurface heat pulse may therefore be unusually loaded. That brings us back to the word that makes this situation feel different: early. Normally, the ocean and atmosphere do not lock together instantly. The ocean may begin to warm cautiously during spring, while the atmosphere hesitates, responding slowly and sometimes refusing to fully join the pattern. Forecasters know this season as a difficult threshold because spring is the hardest time of year to predict what the Pacific will do. They even have a name for that annual uncertainty: the spring predictability barrier. During this window, the ocean is so delicately balanced that models often struggle to see the future cleanly. A careful forecaster in spring has to leave room for doubt, because an apparent El Niño can still weaken or fail to develop. But this year, the system did not wait. The ocean warmed, and the atmosphere connected to it quickly. Winds shifted, storms reorganized, and the whole engine settled into its El Niño configuration, while forecasters would normally still be peering through that spring barrier. By the second week of June, there was little ambiguity left. The advisory was issued. What may be unsettling is not simply that El Niño appeared, but that it appeared on this schedule. The system moved ahead of the usual line. It coupled early, committed early, and did so while running, by every measurement, hotter than models had expected for that point in the year. Consider what an early atmospheric commitment implies. The longer El Niño remains coupled and active, the more time it has to shape the seasons that come after it. If the pattern locks in by mid-June, it has the entire back half of the year to exert influence, to nudge the hurricane season, bend the autumn, and load the winter. If it does not organize until September, several months of influence have already passed. So an early beginning is not just a calendar curiosity. It means the largest climate swing the planet naturally produces has more time available to press on the systems downstream from it. The timing becomes a measure of possible reach, not merely a date on a forecast bulletin. Even the name carries a human memory. Along the coast of Peru, fishermen noticed centuries ago that every few years the cold, fish-laden current that sustained them would turn warm and barren. Long before global maps and modern archives, the fishermen off Peru had a quieter warning system. The anchovies would disappear, the desert would receive rain, and the change often arrived near Christmas. From that pattern came the name El Niño, the boy child, tied to the Christ child whose season it seemed to follow. They had no satellites, no reanalysis extending back to 1940, and no planetary dashboard of ocean heat. What they had were bare nets, altered skies, and a name for a current that could turn abundance into hardship. In a sense, the central lesson was already there. The temperature of one stretch of sea can decide whether a season feels merciful or severe. What has changed is the scale of our vision. The empty nets of that coast have become, in our time, disrupted hurricane seasons and winters carrying unusual weight. So the thread returns to its center. The key point is not simply that the ocean is warm. Warming was expected. And this event had been watched for months. The more striking part is the timing and the connection. The atmosphere and ocean coupled early. The westerly wind burst reached record strength. The subsurface pulse was already heavily charged, and the system committed while it was still supposed to be in the uncertain stage. Warmth was in the forecast. The pace was the surprise. And in a climate story, speed can be the clue that makes everything feel less settled than the averages suggest. To understand why this ocean pattern can reach so far, we need one more piece of the mechanism. Over the warm pool, air rises. Over the colder eastern Pacific, air sinks. Those motions are linked into a vast atmospheric loop along the equator. Air climbs in the west, moves eastward high above, descends in the east, then returns westward near the surface as the trade winds. Scientists call this the Walker circulation, named for the man who first identified the pattern. It is not just background motion, it is the hinge that lets the whole system swing. When El Niño pushes warm water and storm activity eastward, it is not merely shifting rainfall from one patch of ocean to another. It weakens and rearranges that entire belt of moving air. And because the atmosphere behaves as one connected fluid, a major disturbance over the widest ocean on Earth can send consequences outward into the jet streams that guide weather over North America, across the Atlantic, and over continents with no Pacific shoreline at all. This is the simple version of a large idea. A warm region of equatorial sea can help shape whether Texas floods or Spain bakes, because it bends a circulation that much of the world's weather leans upon. The image is almost too gentle for the power behind it, but it helps us see the invisible machinery. Keep the bathtub picture in mind a little longer, because its hidden layer matters for what comes next. Under normal trade winds, warm water piles up toward the west, and the boundary between the warm surface layer and the colder deep water tilts. That boundary is called the thermocline. It lies deeper in the west, beneath the mound of warm water, and it rises closer to the surface in the east, where colder water can more easily emerge. Then, a westerly wind burst changes the balance. It pushes warm water back toward the east, flattening the tilt, driving the warm layer downward in the eastern Pacific and lifting the thermocline in the west. The downwelling pulse described earlier, the buried freight train traveling east beneath the surface, is that flattening motion crossing the ocean out of sight. This is why forecasters pay such close attention to the subsurface. Heat below the surface is heat not yet fully spent. A broad supply of warm water waiting just under the skin of the ocean can become future surface warming if conditions allow it to be drawn upward and spread. This year's measurements show that the reservoir is substantial, which helps explain why forecasters expect the surface warming to continue rather than simply fade. The visible warmth is only part of the story. Below it, there is still more energy waiting to matter. Timing adds another layer to the concern. Because early coupling gives an event something as important as strength, time. The influence an El Niño has on later seasons depends on how intense it becomes, but also on how long the ocean and atmosphere remain linked and operating together. If that lock-in happens by the middle of June, the event gains the entire back half of the year to work through: the hurricane peak, autumn, and the approach to winter. It is like a tenant arriving early and having the house for an extra 2 months. Each early week gives one of the planet's largest climate levers more opportunity to press on hurricane seasons, monsoons, storm tracks, and harvests. So when this event is described as early, that is not a minor calendar note. It suggests extra leverage added to extra strength, all unfolding inside a warmer world. That brings us to the question that vague unease cannot answer on its own. How warm is the water, exactly? How quickly did it get there? And how likely is it that this becomes not merely an El Niño, but one of the giants, an event that earns a permanent place in the record books and reshapes a year of weather around the globe? Forecasters have assigned numbers to these questions, and some of those numbers are the kind that ask to be read a second time. So now we turn to the dials. How hot, how fast, and how likely. Numbers are where drama either becomes evidence or dissolves into background noise. A figure without interpretation is only a sound, so each measurement has to be placed carefully. Scientists do not treat the entire Pacific as one vague temperature average. Instead, they divide the equatorial Pacific into several regions and compare the water temperature in each region with its long-term normal. 4 regions matter, though only 2 need to stay in focus for this story. One box sits in the far eastern Pacific, close to South America. Another, the larger box, lies in the central Pacific, near the date line. The eastern box tells us what the coast is experiencing now. The central box is the foundation of the official index, the measure that determines in the records whether a year qualifies as El Niño and how strong that El Niño becomes. Begin with the eastern box off South America, because it is the most dramatic reading on the board. At the moment, that water is running about 2.1 degrees above its normal. A rise of a few degrees can sound harmless if we imagine a room thermostat being nudged up or down. But this is not a room, and it is not even the air above the sea. It is the average temperature of a vast stretch of ocean, a region comparable in scale to a country, now running more than 2 degrees warmer than it normally would at this point in the year. Water resists heating far more than air does. The ocean is about 1,000 times harder to warm. So when that much seawater is pushed that far above its usual state, the hidden energy behind the number becomes difficult to grasp, and the speed matters just as much as the size. In the second week of May, that same eastern region was only about 7/10 of a degree above normal. Roughly 5 weeks later, it had climbed to about 2.1 degrees. In other words, the anomaly did not merely grow, it more than tripled in a little over a month. That kind of change does not feel like a slow slide. It looks more like a rapid surge, and it raises the first quiet question. What else is moving faster than expected? The view changes slightly when we shift into the central box, the region watched by the official index and the place where the formal language of El Niño is anchored. On weekly measurements, those waters have already passed the threshold associated with El Niño conditions, sitting somewhere between 7/10 and 9/10 of a degree above normal, with the climb still underway. Yet the number that eventually gets attached to a year in the climate record is not based on 1 week alone. It is a 3-month average, designed to smooth out brief, warm spells so that the system is not misread. That measure is the Oceanic Niño Index. For the most recent 3-month season, it stood at about 0.48 of a degree above normal, just shy of the official El Niño boundary of half a degree. But that average still carries the cooler early spring inside it. It is looking backward, while the weekly observations are looking closer to the present moment. Those live readings have already moved beyond the line and are still accelerating, which helps explain why the advisory arrived when it did. The contrast is important. One dial shows the official record catching up, while the other suggests the ocean has already crossed into a different state. To understand why the pace feels so striking, we have to remember where the system began. In the autumn of last year, the same official index was not simply neutral. It was below zero, near -0, 55 of a degree, on the cool side of the scale, carrying the faint imprint of the opposite, the colder phase. From there, season by season, the number rose. It moved from about -0.55 toward -1/3 of a degree, then toward roughly neutral, then through 0 into positive territory. And it continued upward to its current position. Across just 2 seasons, the official 3-month index shifted by roughly a full degree. That is a large swing for a smoothed ocean measure. The system did not creep gently over the boundary. It came from the cold side, crossed neutral, and pressed into the warm side in about the span of a school year. For a calm observer, this is the part that makes the pattern feel less like background noise and more like a transition with momentum. So the present picture has several pieces. The eastern waters are running beyond 2 degrees above normal after tripling their anomaly in 5 weeks. The central weekly data have crossed the El Niño line. The official 3-month index has climbed about a full degree in 2 seasons, starting from a cool autumn. These numbers tell us where the ocean is now. They do not, by themselves, reveal where it will peak. And that next question is where the forecast becomes most unsettling. At this stage, forecasters are no longer mainly asking whether this is an El Niño. That point has effectively been decided. The larger question is how powerful the event may become. There are formal categories for that answer. If the official index peaks modestly, the event is recorded as weak or moderate. If the peak rises above 1-2 degrees, it is classified as strong. If it climbs above 2 full degrees at its maximum, it reaches the highest tier, a very strong event. The kind often described informally as a super El Niño. That is the domain of the largest events, the ones that become reference points long after they fade. The current outlook is the figure worth pausing over. It places the odds of this event reaching that very strong category, with a peak above 2 degrees this coming winter, at roughly 63%. That is not a remote tail risk hiding at the edge of the forecast. In the central outlook, it is more likely than not that the developing event reaches one of the strongest El Niño levels ever measured. Then, there is the upper end of the model guidance. The European model, among the world's leading seasonal forecasting systems, has been pointing its plume towards something near 3 degrees above normal by December. A number like 3 degrees lands differently when placed beside the great events of the modern record. The El Niño of 1997 and 98 peaked at around 2.4 degrees. The 2015 and 16 giant reached around 2.6 degrees. The powerful 1982 and 83 event peaked at around 2.2. Those are the benchmarks that scientists and forecasters still use when describing the most consequential episodes. They were linked to weather disruptions across the planet, tens of billions of dollars in damage, and they remain textbook cases. A peak near 3 degrees would not simply sit among them. By that index, it would exceed them all, which is why the possibility is so sobering. Care is essential here, because dramatic numbers can easily sound more certain than they are. A 63% probability is still a probability, not a promise. The 3 degrees outcome sits at the aggressive end of the model spread, not at the center of every forecast. El Niño events have weakened before after early signs looked impressive, and the spring barrier means forecasts issued at this time of year carry meaningful uncertainty. A careful scientific reading has to include the range, not only the most alarming point on the map. In this case, the lower side of that range still points toward a strong event, while the upper side allows for a record breaker. So the responsible message is not that 3 degrees is guaranteed. It is that the central forecast already leans toward the very strong tier, while one of the best models is openly allowing for a value that would surpass every event in the record, when the cautious middle of the forecast already points toward a giant. Even the less extreme interpretation does not feel especially reassuring. Taken together, the numbers form a single coherent shape. The present readings are warmer than the models had drawn for this date. The eastern box saw its anomaly triple in 5 weeks. The official index rose about a full degree across 2 seasons after beginning on the cool side. The event was declared early, and the forecast for the peak months ahead already favors one of the rarest and most damaging categories. Each detail can be considered on its own, but they all lean in the same direction. The signal is not merely that the ocean is warm, it is that the warming has been rapid, early, and ahead of expectation. And in a system as vast as the tropical Pacific, that may be the most important message of all. Let us slow down over the eastern box, because its acceleration is the kind of detail that can pass by too quietly. In roughly 5 weeks, It rose from about 7/10 of a degree to about 2.1, and that is not a small twitch in a restless system. The ocean is normally the climate's heavy wheel, vast, slow to move, difficult to warm, and just as difficult to cool once that heat is stored. That slowness is part of what makes it protective. Air can lurch from one week to the next, but the sea usually absorbs, delays, and smooths those swings. So, when a country-sized patch of ocean gains around 1.5 degrees of anomaly in about a month, the signal is not merely a passing weather fluctuation. It suggests that the wheel itself is being driven with enough force to overcome its usual resistance on a timescale of weeks, not seasons. The part of Earth's climate system that should be gradual is, in this case, moving quickly. That is why the pace matters. It points again to an event being pushed more strongly than the model guidance had drawn. There is also a measurement nuance here, and it deserves care rather than drama. As the background ocean has warmed across the decades, the average used as a reference cannot remain frozen in the past. If it did, ordinary modern warmth would make year after year look artificially like El Niño. Scientists have accounted for this by refining the index, so it compares the El Niño signal with a shifting modern baseline instead of an outdated one. That is the more responsible method, but it also means the number must be read with context. A positive index today is positive relative to a baseline that is already warmer than the one familiar to an earlier generation. In other words, the same El Niño value now rests upon more absolute ocean heat than that value would have carried decades ago. The gauge is not lying. The platform beneath it has been rising. And when we turn toward history, that distinction becomes central. Over this, place the marine heat wave, because this is the part of the pattern that feels almost visible from orbit. Outside the equatorial boxes, an enormous area of unusually warm surface water now extends from the islands of the Central and South Pacific up toward the coast of Southern California, joining with the familiar El Niño warmth near Peru and stretching toward the dateline. A marine heat wave is, quite simply, an oceanic version of a heat wave, a persistent region of water far above normal. Its effects in the sea can echo what atmospheric heat does on land. It can strain and kill marine life, bleach coral, move the fish that coastal economies rely on, and alter the air above the water, setting nearby coasts up for heat and storms. That larger setting is important. This El Niño is not just a narrow, warm stripe along the equator. It is sitting inside a broader expanse of record warm water, reaching all the way toward North America. That may help explain why its fingerprints are appearing so early and so widely. And from there, we arrive at the hardest question in the story, the one that has been waiting underneath every number. If the event is already warmer and earlier than forecasts suggested, then the models missed something. Not in a way that makes them worthless, and not in some sweeping, catastrophic sense, but in a precise and meaningful one. They undershot. When our strongest forecasting tools underestimate the opening stage of the planet's largest climate event, it becomes reasonable to ask what that mismatch is telling us. What does it mean when reality begins by running ahead of the model? The careful answer is more sobering than simply saying the computers were wrong. A model is not a crystal ball, even though people often talk about it that way. A seasonal climate model is a vast mathematical description of how ocean and atmosphere act on one another, advanced forward in time on some of the most powerful computers ever built. It is not magic, and it is not a hunch. It is physics translated into arithmetic and run again and again. But, like every such translation, it depends on what the equations include and on the resolution at which the system can practically be simulated. When a forecast succeeds, the world has followed the pathways the equations represented well. When it fails, the miss is not just an error, it is a clue that the real system behaved in a way the equations did not fully capture. So, to say this El Niño is outrunning the models is not to blame the forecasters. It is to notice a signal. Think about the moment in which those models had to look ahead. Their spring forecasts were made during the very interval already described. The spring predictability barrier, the most difficult part of the year for seeing the Pacific clearly. Through that uncertainty, the central guidance did foresee an El Niño, but one arriving on a more familiar timetable and developing at a more familiar speed. The ocean did not follow that script. Coupling happened early, warming came faster. The eastern box tripled its anomaly in 5 weeks, and the event entered official territory ahead of the timetable. The useful question, then, is not whether the models were embarrassed. It is what they underestimated. Several possibilities stand out, and each is unsettling in a different way. The first is the wind. The westerly wind burst that helped force this event was, by measurement, locally one of the strongest on record. These bursts are very difficult to forecast more than a couple of weeks in advance. In a sense, they are weather riding over the slower climate signal, and a model built to project a season cannot reliably identify one specific burst before it forms. If the real atmosphere gave the ocean a stronger shove than the forecasts assumed, then the sea would warm more quickly than projected. That is what the observations appear to show. The train beneath the surface was loaded with more force than expected, so it arrives earlier and heavier. The second possibility is the water beneath the event itself. This is the one that should make the room feel quieter, because it does not vanish when this El Niño ends. The background temperature of the global ocean is now markedly warmer than it was during the great events of past decades. The El Niño of 1997 unfolded on a cooler planet. The El Niño taking shape now is not unfolding over an ordinary sea. For many decades, the ocean has absorbed most of the additional heat held in by a warming atmosphere, so the Pacific water being shifted around by this oscillation is already warmer at the start. When the same physical push acts on a hotter system, the resulting numbers can rise higher because the baseline has moved upward. Climate models do include that warmer background, but the difficult part is the fine interaction. Upper ocean heat, wind forcing, and the delicate boundaries that mark the early life of an event. That is where even useful guidance may lose sharpness. In calm terms, this El Niño is being built on a hotter foundation than any before it, and that foundation is not temporary. It raises a quiet but important question. What happens when a familiar pattern begins from unfamiliar conditions? The third possibility is the one that calls for the most caution. It may be that the full mixture now in play, the record wind burst, the heat stored below the surface, the elevated baseline, and the early coupling forms a setup that our models do not handle especially well, simply because they have not had many examples like it. In a limited sense, models are shaped by history. If the past has rarely produced a particular combination, then predictions become less steady when that combination appears again. If 2026 is now assembling something genuinely uncommon, forecasters may be working near the outer edge of experience rather than inside well-tested territory. That does not mean the models have failed or become useless. It means they are being asked a question very close to the boundary of what they have been trained to answer, and their uncertainty is part of the message. The careful scientists are not pretending otherwise. They are saying that uncertainty openly. That honesty matters, because it tells us where confidence ends and where watchfulness begins. So why should any of this matter beyond the intellectual satisfaction of understanding a forecast? Because El Niño does not only alter the Pacific, it can change the temperature signal of the entire planet. The mechanism is simple in outline, even if the system itself is vast. During an El Niño, the broad expanse of warm water spread across the Pacific does not hold all of its energy below the sky. Over months, it releases heat into the atmosphere. The ocean, in effect, exhales. And when the largest ocean on Earth exhales the heat associated with a Tier 1 El Niño, the global average surface temperature can jump. This is the strongest natural year-to-year influence on global temperature that we have. The phrase, "off the charts," begins to make sense here, not as drama, but as a description of what can happen when ocean heat becomes atmospheric heat. We have seen this pattern recently enough that it is part of lived memory. The last significant El Niño helped push global surface temperature into record territory in the years that followed, as the ocean released heat it had stored. At the time, each of those years was described by many as startling, beyond expectations, almost like a sudden step into a different range. That surge did not occur in isolation. It rode on top of the long-term warming trend, like a wave traveling over a tide that was already rising. Now imagine a similar process beginning earlier, intensifying more quickly, and adding its El Niño pulse onto a baseline warmer than the previous one. In practical terms, that is what off the charts points toward. It is not merely about breaking one record. It is about an El Niño-shaped release of heat arriving early, above a background that is already record warm. These influences do not neutralize each other, they combine. If an event loads its beginning toward the front, it may also bring forward part of that heat release, increasing the possibility of an earlier and sharper rise in global temperature from the back half of this year into the next. The timing in this sense becomes part of the warning. Let us draw the thread back together, because the machinery can become so detailed that the central point starts to blur. The argument here has been the same one seen from several angles. The models underestimated the opening stage of this event. They may have done so because of the wind, the charged subsurface ocean, the hotter baseline, and perhaps a rare combination of factors that has not been tested often enough. That particular miss matters because the same forces that caused the onset to run ahead of the forecast also help shape the eventual peak. And the peak is what determines how much heat is released into the atmosphere shared by the entire planet. So when the speed of this event is described as the warning, the meaning is very specific. The fast start suggests that our forecasting tools may be operating near the limit of their predictive reach. Just as Earth's largest natural climate event builds over the warmest ocean in the instrumental record, that is the reason to keep watching. The pace itself may be telling us that the system has moved into unusually demanding territory. To make the global temperature link clearer, it helps to look at the other side of the oscillation. During the cool phase, the opposite of El Niño, the Pacific quietly helps hold global temperature down. Cold water is drawn upward over a vast region of ocean, and that cooler surface takes heat from the atmosphere. The global average can be held slightly lower during those periods. These are the years when some people point at the thermometer and claim warming has paused. But the pause is an illusion. The heat has not vanished. It has been stored in the ocean. This distinction matters because it explains why the planet does not always warm in a perfectly smooth line. The energy is still in the system, but the ocean decides, for a time, where much of it sits. El Niño is the returning side of that exchange. It suppresses the upwelling, spreads warmer water across the surface, and allows the ocean to give back heat it had been holding, releasing it into the air over the months that follow. Because of that, global temperature often climbs in steps rather than as a steady slope. The cool phase restrains the rise for a while, and then El Niño can arrive and lift the whole planetary average abruptly. This stepped pattern can feel sudden, but it comes from the rhythm of the ocean atmosphere system. In a sleep-quiet way, the Pacific is not only a place on the map, it is part of the planet's temperature machinery. That is exactly what made the recent period so unsettling for people who study this for a living. When the previous El Niño released its heat, the global average surface temperature did not simply edge upward. It surged into records, month after month, by amounts that left many researchers publicly puzzled. Scientists debated why the jump was so large, with El Niño as the main driver, and additional discussion about what else might have amplified the rise. For tonight's point, the details of that debate are less important than the broad lesson. We have just lived through an example of El Niño pushing the global thermometer to surprising heights as the ocean exhaled. And now another one is beginning earlier, moving faster, and forming on a baseline hotter than last time. If the onset is front-loaded, the exhale may be front-loaded as well. That raises the real possibility that the steepest part of the next temperature step arrives sooner, extending from the back half of this year into the next, layered on top of records the previous event already helped set. I want to keep the uncertainty in clear view here, because this is exactly the part of the story where it would be easiest to say too much. Once a narrator overstates what the evidence can support, trust becomes very hard to recover. So, I am not going to tell you that 2026 or 2027 must become a new global temperature record. That outcome depends on several moving pieces: how powerful this El Niño becomes, the precise timing of its peak, and the difficult forecasting details that have already proven capable of wrong-footing the models. What can be described more responsibly is the shape of the setup, and that shape is not gentle. When an El Niño grows larger and arrives earlier, it tends to lift global temperature more strongly and sooner, especially when it is rising from a planet that is already warmer. The central forecast is already leaning toward the larger side of the range. So the honest statement is not a promise that one specific year will break the record. It is a warning about a system with the odds heavily loaded. The lever is powerful, it has been pushed early and hard, and what it raises is not a local thermometer, but the temperature signal of the whole Earth. Still, from the beginning, I said this would not remain only abstract. A line climbing above 1,940 on a chart can feel unsettling, but it is still only ink, pixels, and distance. The purpose of Calm Space is to follow that line beyond the graph, down onto real ground, toward a coast, and into a forecast that anyone can open on a phone. That matters because a record-warm ocean does not have to wait for winter to become part of human life. It is already searching for the nearest shoreline where its energy can be translated into weather. This week, that shoreline is in the United States, along the Gulf of Mexico. And what is taking shape there looks like the first bill coming due for the warmth we have spent 4 parts measuring. So now, let us move from the Pacific signal to what it is already helping us understand about America. Part 5 begins with the Gulf. Far away, near the dateline, the Central Pacific is breaking records. But much closer to home, a coastline is preparing to feel what a warmer ocean world can mean at street level. The timing is unusually stark. As this is being recorded, the Gulf of Mexico and the Texas coast are facing a setup that the National Weather Service has described, in official writing, as carrying the potential for life-threatening flash flooding. That phrase is not an embellishment. Life-threatening flash flooding is appearing in a government flood watch right now. It is worth slowing down over how those words ended up there, because this is one of the clearest and quickest ways to see the central idea of the entire story. Ocean temperature helps write the weather that reaches the coast. When the sea is running hot, that writing can become dangerous. The ingredients are not mysterious, but together they are powerful. A trough of low pressure has been lingering over northeastern Mexico, creating a loose, disorganized circulation of moisture and rising air. At the same time, a front has moved down toward the Gulf Coast and is slowing, turning into an almost stationary boundary. Storms can then travel along that boundary repeatedly, like cars on a train passing over the same section of track. Above and through all of this is the air itself, carrying an extraordinary supply of water. Forecasters describe that supply with a measurement called precipitable water. In plain terms, it asks a simple question. If the whole column of air above one location were wrung out like a sponge, how many inches of rain could fall from it? Over southeast Texas right now, that value is near 2.3 inches. For this date, that is beyond the record. The air above that coastline is holding more moisture than it has on almost any mid-June day measured there. The sponge is filled to the limit for this time of year, and the atmosphere has found the machinery to squeeze it. Combine a stalled front that organizes repeated storms, a trough that helps lift the air, and a record moisture supply available to rain out, and you get the setup the Weather Prediction Center has placed under a level 3 of 4 risk for excessive rainfall. That is the second highest category they issue. Forecasts are discussing rainfall rates of 2 to 5 inches in a single hour inside the stronger cells, along with totals capable of turning roads into rivers and low water crossings into traps. That is why the official language keeps returning not to inconvenience and not to nuisance, but to life-threatening conditions. And this is not merely a future scenario. Emergency managers in parts of the South Texas border region have already reported water rescues and evacuations as the first rounds of storms move through. Flood warnings are not hypothetical marks on a map. They are now the most common alert across the national map today. Here again, discipline with uncertainty matters. Calm space should not survive by making claims that sound dramatic, but outrun the science. So, I am not going to say that the record-breaking El Niño in the Central Pacific somehow reached across 2 oceans and directly caused the Texas storms this week. That would be too neat, and it would be wrong. The immediate cause of the Gulf event is the local pattern, the stalled front, the trough, and the deep moisture in place. But there is a connection here that is real, and it deserves attention precisely because it does not require exaggeration. The air over Texas can carry a record moisture load because the world and the water feeding that air is warmer than it once was. A warmer atmosphere can hold more water vapor according to a fixed and well understood physical rule, and a warmer Gulf can evaporate more moisture into that air. The same broad warmth showing up so loudly in the Pacific is also part of the background that has filled the sponge over Texas to record levels. These are not the same storm, they are the same world. One way to picture it is this. The El Niño in the Pacific may be the loudest single voice in the choir, but the choir around it is carrying the same note, and that note is a warmer ocean. When a record appears in the Pacific, it is the clearest evidence of a condition that is not confined to one basin. It also includes the Gulf of Mexico, where that condition is now being expressed as a record moisture load above a heavily populated coastline. So the Gulf this week should not be treated as proof that El Niño caused a flood. It points to something broader and perhaps more enduring. Ocean temperature is not an abstraction that can be left safely on a graph. It helps determine whether Tuesday's rain is 1 inch or whether the heavier cells produce 5 inches in an hour. It is one of the dials, and this week, along an American coast, that dial is being read in real time as warnings spreading across a map. Beneath the immediate flood threat, there is another signal that skilled forecasters are quietly tracking, and it links 2 oceans more closely than it may first appear. The disturbance near northeastern Mexico is not being monitored by the National Hurricane Center for rainfall alone. As it moves in the direction of the Texas coastal bend, it has been assigned roughly a 30% chance of becoming a tropical system. That number is modest, but it is meaningful. It hints at the character of the season before the season has fully gathered speed. If a ragged trough can even begin to flirt with tropical organization over the Gulf in mid-June, then the water beneath it is already offering usable energy. The Gulf is warm enough, early enough, for development to be considered, and that heat belongs to the same broader ocean warmth that has been showing up in the measurements all along. So this week gives us the close-up view, not an abstract chart, but a scene of sandbags, watches, warnings, and communities preparing in real time. A moisture-laden atmosphere, a warm Gulf, a stalled front acting like a focusing rail, official wording about life-threatening flooding, and a 30% chance that the whole unsettled area tries to consolidate near the Texas shoreline. This is what a warm ocean can mean for America in the short term. In practical terms, measured in flooded roads, evacuations, and bags of sand, it may feel like an early invoice delivered to the nearest coast the warmth could reach. And that raises the larger question. If this is only the opening signal, what does the wider pattern look like? Pull the view back, and Texas stops looking like a lone point of trouble. It becomes the sharp edge of a much broader design. Across the national weather map today, the most common alert is not for heat, wind, or severe thunderstorms. It is for flooding. Rivers are already running high over a large part of the central United States, and sections of the Guadalupe, the San Antonio, and smaller rivers and creeks across south and central Texas are forecast to climb to moderate flood stage. That is the threshold, where water no longer stays politely inside its banks. It begins reaching roads, fields, and the margins of towns. Farther east, another flood watch stretches across southeast Louisiana, extending the concern into the lower Mississippi Valley. The result is a wide corridor of saturated soil, swollen waterways, and air so moisture-heavy that it can keep feeding repeated downpours. The Gulf Coast is therefore not simply waiting out one rough afternoon. It is under a pattern that can reload again and again. In a calm satellite view, this might appear as bands of cloud and vapor. On the ground, it becomes a slow accumulation of risk. The reason this setup produces such dangerous rain is rooted in simple atmospheric physics, and it leads back to the warmth of the ocean. Storms forming along the Gulf Coast right now contain what forecasters describe as a tall, warm cloud layer. In other words, a deep part of the storm remains above freezing, allowing the cloud to turn water vapor into raindrops with remarkable efficiency. When the inflowing air is both warmer and wetter, that rain-producing layer can become deeper, and more of the extraordinary moisture in the column is wrung out quickly as heavy rainfall, instead of remaining suspended higher in the storm. The same ocean warmth that fills the air like a soaked sponge can also help the storm squeeze that sponge harder. That is why forecasts can include rainfall rates of 2 to 5 inches in a single hour. This is not merely an ordinary thunderstorm lingering a little too long. It is a more efficient rain engine, powered by warmer, wetter air and held over the same places by a stalled boundary. Seen this way, the forecast numbers are not just technical language. They are a warning that the atmosphere has become unusually good at turning ocean-fed moisture into water on the ground. And already, that water is affecting people, which is where the story must not be allowed to drift into abstraction. Along portions of the South Texas border, emergency managers have reported water rescues after early rounds of storms dropped several inches within only a few hours. People have had to be pulled from vehicles and low-lying areas. Flash flood warnings, the urgent alerts that mean people should move to higher ground immediately, have been issued across the region. This is the human meaning behind a record value on a graph. When precipitable water is at a record level and rain rates can reach 5 inches in an hour, the translation in the hardest hit places may be a family stranded on the roof of a car in darkness, waiting for a rescue boat. That chain of events from ocean temperature to atmospheric moisture to a flooded road is precisely the kind of connection Calm Space is here to follow. Tonight, that connection is not theoretical. It is unfolding along an American coast. Return for a moment to that 30%, because it is a small figure carrying a larger message. A 30% chance is not a prediction that a storm will form. It is about a 1 in 3 possibility, which means the more likely outcome is still that this feature remains a disorganized, rain-heavy trough rather than becoming a named system. Yet the fact that the National Hurricane Center is watching part of the Gulf in mid-June, weeks before the basin usually becomes more active, says something important about the energy available in the water. A tropical system does not need to form for the point to matter. The point is that the Gulf is already warm enough, this early, for organized tropical development to be placed on the table at all. That is one way the warm ocean world reveals itself. And if a June or July system does manage to organize over water this warm and this full of stored heat, then the danger of rapid intensification becomes part of the conversation. That is the possibility of a storm strengthening much faster than older expectations might suggest, with a populated coastline in its path. So the trough is worth watching whether it spins up or fades away. Either outcome still offers a live demonstration of the larger pattern. Sea surface warmth is weighting the odds for the season, and those odds are already being tested near the Texas coast. Hold on to the phrase, "the first invoice," because it helps frame what comes next. The Gulf this week is the immediate expression of the pattern, a warm ocean world presenting its cost to one coastline over several days. But an El Niño does not mainly operate on the scale of days. It works across seasons. The Gulf flood is the first note, the event visible from the window this week. The larger bill, the seasonal one that El Niño is now shaping across the American summer and into the winter beyond, is broader, stranger, and in one key way, genuinely counterintuitive. The same El Niño that might seem, at first glance, as if it should make every storm worse is about to influence one of the most important basins in a way that can look almost like relief. Before we arrive there, the thread needs to be gathered back together. The Pacific is the master dial. This week, one of its readings is appearing as a flood watch in Texas. Over the months ahead, that same dial may express itself across the entire country in ways that are less immediate, but no less important. And part of that signal may surprise us. Part 6. Across the Pacific, summer is quietly taking shape. If the Gulf is offering the first note this week, then the months ahead may become the larger composition, and El Niño is one of the rare planetary scale patterns powerful enough to steer weather across a continent for many months at a time. So the question is not simply whether conditions become worse everywhere. The more useful question is where the atmosphere may lean wetter, where it may turn quieter, and where the ocean's warmth could change the odds in surprising ways. This is the calmer, more honest version of the season. There may be winners and losers, and understanding that difference can turn alarm into perspective. Begin in the southwest, where another seasonal threshold has just arrived. In the middle of June, the North American monsoon officially begins, opening the period when moisture is drawn northward into Arizona, New Mexico, and the broader southwest, helping to ignite the afternoon thunderstorms that mark desert summer. In a typical year, that monsoon reaches its strongest rhythm from the middle of July into the middle of August. But this year, it is entering a Pacific basin that is being reshaped by a developing El Niño. The Eastern Pacific connection may add moisture to the monsoon, shift its timing, and alter how intense those storms become. Few places show the ocean-atmosphere link as plainly as the desert southwest, where a change in the Pacific can echo as thunder over neighborhoods far inland. This year, the ocean dial appears set in a way that could give the monsoon more energy, while also making its behavior more difficult to anticipate. Just offshore, the Eastern Pacific hurricane season offers an even clearer view of what a warmer ocean can do. That basin has already generated multiple named storms this year, moving through the early part of the seasonal name list, with several forming off the coast of Mexico, near Oaxaca and Acapulco. Up to now, most have remained relatively modest, either subtropical or close to tropical storm strength. Yet forecasters are watching the coming weeks with caution. The water is warming, and the zone of disruptive wind shear from Baja down toward Acapulco is beginning to weaken. That combination matters because tropical systems thrive when warm water lies beneath them and hostile upper winds relax above them. Under those circumstances, intensification can happen quickly and sometimes dramatically. Over the past decade, the lesson has been difficult. Storms moving over extremely warm water can undergo rapid intensification, leaping several categories in a single day and leaving both forecasters and coastal communities with very little time to respond. The research around this trend is unsettling, and Calm Space has explored it before while covering the seasonal setup and the monster typhoons earlier this year. Rapid intensification near coastlines has been increasing, and the Eastern Pacific is now lining up with the kind of conditions that can support it. So, the next systems near Mexico may not remain gentle. Borderline storms. Some could fade into the night as tropical storms and emerge by morning as major hurricanes. That possibility is not a prediction for every storm, but it is the risk the atmosphere is beginning to place on the table. Trace that same warm water northward, and the story reaches California, where the ocean is already influencing the coast even without a landfalling storm. The marine heat wave described earlier, a broad tongue of warm water stretching from the South Pacific towards Southern California, is now pressed against the west coast. Warmer water near shore can reshape the air immediately above it and add stress to the marine ecosystems below. At the same time, it has arrived with an unusual sequence of large swells, with waves reported in the range of 9 to 15 feet, striking parts of the Hawaiian and California coasts. Those waves have been powerful enough to move sand, damage property, and tug at structures built too near the shoreline. Not every swell can be pinned directly on El Niño. Some are born from distant storms and travel across the ocean long before they arrive. Still, the warm coastal water and the energized Pacific belong to the same broader seasonal picture. They may be offering an early glimpse of a winter pattern in which the west coast often finds itself exposed to incoming Pacific storms. In a sleepier view of the ocean, waves may seem like background motion, but here they become signals, hinting at how much energy the basin is holding. Now comes the part that often sounds backward at first. A record-breaking El Niño does not automatically mean a monstrous Atlantic hurricane season, even though the ocean is warm and hurricanes feed on warm water. The Atlantic responds differently when El Niño is strong, and the reason is one of the more elegant pieces of climate science. As the Pacific warms and storm activity shifts toward the central Pacific, the upper-level wind pattern changes far downstream, extending its influence toward the Atlantic. In particular, a strong El Niño tends to increase high-altitude wind shear over the tropical Atlantic. Those fast winds aloft can tear at the tops of developing hurricanes, disrupting their structure before they fully organize. In that sense, a strong El Niño usually works as a brake on the Atlantic hurricane season rather than an accelerator. The same Pacific event that may provide fuel to the Eastern Pacific can, across the oceanic divide, help suppress the Atlantic later in the season. That contrast is why the seasonal map is more nuanced than the simple phrase, warm water means more hurricanes. The atmosphere is not responding to one ingredient alone, it is responding to how the entire pattern is arranged. Even so, that potential relief has limits. It is not a promise, and it should not be treated like protection. The El Niño break is a broad, late-season tendency across the basin, not a guarantee for any particular week or any single storm. The Gulf this week shows why caution is necessary. A warm, homegrown system can still develop close to shore even when the overall Atlantic season is being held back. And if one storm does manage to form over very warm water near land, it can still become catastrophic because there may be so little room and time before impact. So, the clearest summary is not that the Atlantic is safe. A better summary is that the seasonal balance is tilted toward fewer Atlantic storms overall, while also leaning toward more and stronger storms in the Eastern Pacific, with the important warning that any Atlantic storm that breaks through may still be severe. It is less tidy than a headline, but it is closer to the truth. In weather, the averages can whisper one story while a single storm tells another, and both have to be held in mind at the same time. Move the clock ahead into winter, and the pattern begins to resemble the classic strong El Niño signature over the United States, the one built into decades of records. An energized subtropical jet stream tends to carry one storm after another into California and then across the southern tier of the country. That setup raises the risk of atmospheric rivers, flooding, and mudslides along the west coast, while also favoring wetter and stormier conditions from the southwest through Texas and the Gulf states into the southeast. Farther north, the Pacific Northwest, the Northern Plains, and the Upper Midwest often lean milder and drier than normal. The result is a continent divided by the position of the jet, the south more frequently under the storm track, the north comparatively quieter and warmer. This is not a map of certainty, but it does describe the seasonal pressure being applied. And as El Niño continues to organize the Pacific, the atmosphere above North America may keep translating that distant ocean warmth into very different weather from one region to the next. If this El Niño rises into the very strong category that forecasts are leaning toward, then the winter signal over the United States could become much louder. California, in that case, may not simply have a wet season, it could become one of the main storm targets of the cold months. So now the pieces of the American picture come together. The southwest monsoon enters a Pacific basin that has been rearranged. In the eastern Pacific, hurricane season gains energy from unusually warm water while wind shear weakens. Along the west coast, a marine heat wave presses against the shoreline, helping turn distant storms into damaging swells. Over in the Atlantic, the story is stranger. The basin may be somewhat restrained, even while the warm Gulf still leaves room for a dangerous system to form close to home, like the one threatening Texas right now. Then winter points toward a southern tier that is wetter, stormier, and more flood-prone, while the northern tier trends mild and dry. None of these signals stands alone. Each one can be followed back through the moving gears of the atmosphere to the ocean temperatures we have been tracing from the beginning. This is where a number on a map becomes a season in real life. The Pacific acts like a master control, and the response appears region by region, month by month, across the country. It is worth lingering on rapid intensification, because few hurricane behaviors are more dangerous when a storm is approaching land. Over the last decade, it has changed the way risk has to be understood. The older mental image was simpler, a hurricane slowly strengthening over several days, giving coastal communities time to watch, prepare, and decide. Rapid intensification disrupts that rhythm. When a cyclone moves across water that is not only hot at the surface, but also warm deep enough for the storm to stir, the system can tap into an unusually rich supply of energy. Under those conditions, winds may jump by 30, 40, or 50 miles per hour in just one day. Research has been pointing in an unsettling direction. These explosive surges have become more frequent, and more of them are occurring near the coastline during the final day before landfall. That is the most unforgiving combination. The storm is strengthening fastest at the moment when evacuation time is shortest. This is why the Eastern Pacific setup matters so much. Warm water and weakening shear are exactly the ingredients that can open the door to those sudden leaps, and that is why forecasters are cautioning that the next storms off Mexico may behave very differently from the weak early systems seen so far. In a calm forecast graphic, that may look like a technical detail. For people on the coast, it could be the difference between warning and surprise. Now lift the view away from the shoreline and look inland, across fields and harvests. One of El Niño's largest, and often least discussed, signatures is written into global agriculture. The pattern is not simply bad everywhere or good everywhere. Instead, it tends to divide the world into regions that gain moisture and regions that lose it. A strong El Niño often pushes certain breadbaskets toward dryness in a fairly repeatable way, including parts of Southeast Asia, India, Australia, Southern Africa, and northern parts of South America. Other areas may lean wetter, with parts of the Americas sometimes receiving useful moisture. The risk researchers point to is not just one drought in one place. The deeper concern is that several major grain-growing regions could face stress in the same year. because one ocean signal is influencing many of them at once. The modern food system can often absorb a single regional failure through trade and reserves. So this is not a forecast of famine, but that safety cushion depends on a quiet assumption that distant bread baskets will usually fail at different times, allowing a shortfall in one region to be offset by abundance in another. A powerful El Niño is one of the rare climate patterns that can place pressure on multiple regions during the same season. That is the part to watch carefully, not as a prediction of catastrophe, but as a reason food prices and supply chains may become unstable in the year after a major event, especially for poorer countries that depend on imported food. In that sense, the ocean's warmth can end up echoing far from any coastline. Bring the focus back down to the ground beneath your own feet, because winter is where many people in the United States may feel this pattern most directly. If this event reaches the very strong tier favored by the forecasts, the classic outcome would steer repeated Pacific storms into California during the cold season. These can arrive as atmospheric rivers, long corridors of moisture capable of delivering a season's worth of rain in a week. At first, that can refill reservoirs. Then, if the storms keep coming, the same water can saturate hillsides until mudslides become part of the story. Farther east, the southern tier of the country, from the southwest through Texas and the Gulf states into the southeast, would tend to be wetter and stormier than normal. The northern tier, by contrast, would more likely lean mild and dry. It is as if the continent is divided by the placement of one jet stream, with that river of air helping decide who receives storms and who is left under calmer skies. And the position of that jet is shaped in large part by the water temperatures we have been following since the first minute. The explosive hurricanes, the stressed harvests, the flood-prone California winter. Each is another downstream reading from the same master dial. The pattern may look scattered when viewed locally, but from above, it begins to resemble one connected system. Yet the United States is only one region reading the signal. The story now widens to the hemisphere, and then beyond it. At the same time that the Pacific is breaking records and the Gulf is flooding, another part of the world is facing heat. Western Europe is moving into a heat wave that forecasters are describing with unusually severe language, the kind normally reserved for dangerous events. Temperatures are expected to climb toward 40 degrees on the Celsius scale. That is not ordinary summer discomfort. It is heat capable of killing. And this is the question that ties the next part of the story to everything already discussed. Are these separate crises that simply share the same season? Or are they different expressions of a wider pattern, spoken in different ways across different continents, with the same warming ocean beneath them? The question does not require a simple answer to matter. It invites us to watch the atmosphere not as isolated weather, but as a linked system where distant extremes may be connected by deeper forces. So turn the globe toward Europe, Part 7, 3 continents, 1 ocean. While the Gulf is flooding and the Pacific is setting records, Europe is entering its own emergency. Across Western and Central Europe, a heat wave is strengthening, and meteorologists are using words chosen with care. Forecasts show temperatures climbing beyond 30 degrees C over broad areas, rising above 35 inches, the hottest zones, and in some places reaching toward 40 degrees. For anyone thinking in Fahrenheit, 40 degrees C equals 104 F. That level of heat does more than make a day uncomfortable. It can become deadly for the old, the sick, and those who are not prepared. One forecaster examining maps for the southern part of the continent indicated that there, temperatures were effectively expected to remain above 30 degrees before July, with many days reaching 40. Pause on the severity of that. A heat wave is not only a number on a chart, it is a pressure placed on bodies, buildings, and routines. And it raises a stark question about how much stress a summer atmosphere can hold. It is not only the afternoons climbing toward 40 or the nights that will not cool below 30 that make this heat so oppressive. It is the persistence, the sense that the atmosphere has settled into place and stopped offering relief, hour after hour, for weeks. Behind it sits a broad rotation of low pressure over the North Atlantic, and its behavior should feel familiar after the last 6 parts. It is helping pull hot air northward from Africa and Iberia, then holding that heat over Europe instead of letting it sweep away. Forecasts suggest that one surge could reach as far north as Finland around midsummer, the festival tied to the longest days of the Scandinavian year. On the temperature maps, the deep red heat over southern Europe and the violet pockets of the hottest air higher in the atmosphere are not just dramatic colors. They show a pattern that has become trapped, a configuration of the air that lingers over the same land long enough for warmth to build into something hazardous. This is the part where care matters. Calm space should not earn your attention by turning every map into a simple cause and effect story, because the atmosphere rarely works that way. El Niño did not directly cause the European heatwave. There is no clean line running from the Pacific record to a thermometer in Spain, and drawing one would be misleading. The nearer explanation is regional, an Atlantic blocking pattern, the shape of the jet stream, and the ordinary weather machinery of a continental summer, arranged in an unusually dangerous way. A calm reading of the science asks us to hold 2 ideas at once. The local trigger matters, and the broader background matters too. The European heatwave, the Pacific record, and the Gulf flood are not one event, and they are not beads on a single causal chain. Yet they can still be read as expressions of the same larger condition, a planet whose oceans and atmosphere now contain more heat than before. When the baseline rises, any blocked pattern that appears has warmer air available to trap. A summer blocking high over Europe is not, by itself, an alien feature. What becomes abnormal is the intensity it can achieve when the air under it began warmer, and when the seas feeding the continent's weather are themselves at or near record warmth. The same broader logic applies to the heat affecting North America. Just yesterday, Calm Space was examining the Pacific Northwest as it broke its own heat records in a region that learned a few years ago, in the most lethal way, how dangerous a stuck heat dome can become over an already warmed world. Europe today, the Pacific Northwest yesterday, the Central Pacific Ocean throughout the month. 3 regions, 3 separate immediate mechanisms, and 1 shared background state. That is why Europe belongs in a discussion centered on the Pacific, even though the Pacific did not simply cause the European event. It helps show that this is not just a remote ocean behaving strangely in isolation. Once the view widens, and heat appears across several continents in the same season through different local pathways, the picture begins to look less like a random collection of misfortunes. It looks more like a surface response appearing in many places at once from an underlying shift. Among the controls shaping that surface response, Pacific temperature is the largest and most forceful one we can name and measure. Europe becomes the corroborating signal, while the Pacific remains the great measurable driver in the background. The continental heatwave is not proof of a single direct arrow, but it does suggest that the ocean signal being tracked has a planetary reach. The language surrounding these European maps also deserves a pause, because words shape how we carry fear, risk, and uncertainty. Some posts online describe the heat with phrases such as climate monstrosity and climate emergency, and they ask what part of the emergency people still fail to understand. That concern should not be dismissed. The heat is genuinely dangerous, and the maps point toward a serious, possibly historic situation in both Europe and the Pacific. Still, Calm Space has a responsibility to separate what the data shows from the emotional force it produces. Forecast maps showing 40 degrees are projections of where heat may go, not records of days that have already occurred. The final strength of El Niño is also probabilistic. a 63% likelihood of reaching the top tier, not a settled outcome already carved into the future. The most responsible position is therefore neither denial nor certainty of catastrophe. It is to say that the risk is real, the scale is large, and the outcome still carries uncertainty. Anyone presenting the future with no error bars is offering a story that has been made too neat, whether that story is selling reassurance or doom. One last thread needs to be handled gently, because many viewers may feel it forming in the back of the mind. When events grow this large and strange, when the ocean breaks, records 5 days in a row, and 3 continents are under extreme heat at once, explanations begin to circulate that claim something so vast cannot be natural. It must, they suggest, be engineered, manipulated, or deliberately produced. The instinct is understandable. The human mind often searches for an author behind disaster, because an authored disaster can seem less frightening than a systemic one. If there is an author, perhaps the author can be found and stopped. But the science does not support that interpretation, and pretending otherwise would be unfair. El Niño is one of the most carefully documented natural phenomena on Earth, recorded in coral, in sediment, and in the empty fishing nets of past centuries, long before anyone could have engineered such a thing. The added background heat, the warmer baseline that makes each event more intense, is explained by the measured physics of gases in the atmosphere, not by a hidden hand operating a control panel. The more difficult answer is also the more honest one. There may be no single author to catch. There is a system we have nudged, and it is responding according to physics, perhaps faster than many expected. That is why the stuck pattern matters so much. It is not merely heat that creates the danger, but heat held in place long enough for the landscape, the buildings, and the human body to run out of ways to release it. It is the same antagonist that has been appearing throughout this story, only wearing a different mask. The jet stream, that swift corridor of wind dividing cold northern air from warmer air to the south, is not a clean, steady line across the map. At times it bends into enormous waves, pushing far north in one place and plunging south in another. More troubling still, those waves can stop moving. Instead of sliding onward, they can linger for days, or even weeks, holding the atmosphere in a fixed position. When one of those northward bulges becomes a summer ridge of high pressure and settles over land, the result is a quiet but relentless trap. Skies clear, sunlight falls without much interruption. Air sinks, compresses, and warms, and the whole pattern resists being moved along. Heat then accumulates, one day stacked upon the next, with no easy escape route. That is the basic shape of a heat dome, and that is what is now organizing over Europe. In a broader sense, it belongs to the same class of stalled atmospheric patterns that brought lethal heat to the Pacific Northwest a few years ago, and then returned in a milder form just this past weekend. What matters most is not one brutal afternoon on its own. The deeper danger is a weather pattern that stays put. That distinction may sound small, but it is often the difference between hardship and disaster. A single hot day can be endured. A locked-in sequence begins to narrow every margin. There is one detail in the European outlook that deserves special attention, because it is often the detail that does the most harm while receiving the least notice. The headline is not simply that afternoon temperatures may climb to 40 degrees C. The more alarming signal is that, in the south, nighttime temperatures are not expected to fall below 30 degrees, 104, and a sweltering 86 Fs. Human beings often survive dangerous daytime heat because the night offers a chance to unload it. As temperatures drop, the body can release some of what it absorbed under the sun, but when the darkness remains hot, that reset never really arrives. Heat stress carries forward into the next day, and then the next. For older people, for the sick, for infants and young children, and for anyone without a reliable way to cool down, the danger can build silently inside homes after sunset. The deadliest heat waves often do not announce themselves with one cinematic afternoon. They do their damage through repeated nights that refuse to loosen their grip. That lesson was carved into memory during the Pacific Northwest disaster a few years ago, and it was revisited on Calm Space just yesterday. The number after midnight is the one that may matter most. In the stillness of a warm night, the atmosphere can become less like weather and more like a weight. It is also worth returning carefully to the idea of an engineered disaster, because the question is not always asked in bad faith. Some of you may still be weighing it, and it deserves more than a wave of dismissal. The feeling that an event this large must have been designed is understandable. It is a very human reaction to scale, but size is not proof of intention. This event is enormous, precisely because it belongs to the planet's own coupled machinery, the Walker circulation, the thermocline, and the trade winds moving through one of their largest natural modes, now doing so on top of a warmer baseline. No control panel is required to make that happen, and no control panel could produce it. The harder truth is not that someone built a machine to create this on purpose. It is that the temperature of the entire system was nudged upward, a little, almost everywhere, and then the old rhythms of the ocean and atmosphere began to return with greater force. There is no hidden author to locate. There is physics, responding in ways we helped accelerate and may not have fully expected. That may be less satisfying than a plot, but it is also more important, because it leaves us facing the system itself rather than an imaginary operator behind it. So the thread comes back together. We have followed it across a hemisphere, and now the shape of the story is clear enough to tie. The Pacific is acting like the master dial. We have seen it set records. We have seen its energy pay out along the Texas coast. We have watched it prime the American summer, and now its signal appears again, echoed and corroborated in the deadly heat of a European June. This is no longer just a distant ocean doing something distant. It is a planetary condition, with the Pacific speaking the loudest. Yet a condition this large naturally raises a deeper question, one that the latest measurements alone cannot settle. Has the ocean behaved like this before? Is there a precedent for a swing this powerful? And if there is, what happened to the people who were forced to live inside it? To answer that, we have to step out of the present and move backward, into the era of the giants, into the years that still make the old records seem uneasy. Now we turn to the ghosts of El Niño's past. Part 8. The ghosts of El Niño's past. History does not reproduce weather, event for event, but it echoes strongly enough that ignoring it would be careless. The record of the great El Niño events is one worth approaching with caution, perhaps even with a little fear. The atmosphere may not repeat itself exactly, but the patterns it leaves behind can still speak. First come the giants, the events that earned permanent places in the record and remain the measuring rods for the present year. When forecasters warn that this event could rank among the strongest ever observed, these are the comparisons sitting in the background. To understand the force of that statement, we have to remember what those past events did. The most recent monster was the El Niño of 2015 and 2016, which peaked at around 2.6 degrees above normal in the Central Pacific. It helped lift global temperatures to what were then record highs. It was linked with severe drought in parts of Africa, Southeast Asia, and Central America, with food shortages that pushed tens of millions of people into crisis, with coral reefs turning white across the tropics in a historic scale die-off, and with a chain of weather disruptions that reached nearly every continent. That is what one of the strongest versions of this ocean pattern can look like when translated into human terms. It is not only a number in the Central Pacific. It becomes water missing from fields, heat trapped over land, and stress spreading through systems that were already fragile. Then, a little farther back, there was the great El Niño of 1997 and 98, which peaked near 2.4 degrees, 4 degrees. That event reshaped a winter across the Americas, brought deadly floods and landslides, intensified wildfires in drought-stricken regions on the far side of the Pacific, and caused tens of billions of dollars in damage around the world. Before that came the powerful 1982 and 83 event, peaking around 2.2 degrees, which caught the world with less preparation and is still examined for the breadth of disruption it produced. These are the benchmarks. This is the behavior of a top-tier El Niño. And, as you may remember, the forecast for the event developing now already favors that category, while the most aggressive guidance points somewhere beyond all of them. That comparison should be handled carefully, but it should not be softened into comfort. If the present is being measured against these names, then the scale of concern is already substantial. Still, if we want to understand the possible upper reach of this oscillation's impact on human beings, we have to travel much farther back. We must move past the satellite era, past the period of reliable thermometers, and into the 1800s, toward an event Calm Space has explored before and will only touch on briefly here as a deliberate callback, because it deserves its own full telling and has already received one. In 1877 and 1878, the planet experienced one of the most powerful El Niño events found in historical reconstruction. It also coincided with a constellation of other ocean anomalies, combining into something close to a worst case. The outcome was not merely a difficult season, it became a catastrophe with few equals in recorded history. Across Asia, monsoons failed. Across India, China, Brazil, parts of Africa, and beyond, drought tightened its hold, and harvests failed on several continents in the same span of time. The famines that followed, according to the most frequently cited scholarly estimates, took well over 50 million lives. 50 million is almost too vast for the mind to hold, and that is precisely why it should not be allowed to fade into abstraction. It marks an upper boundary in recorded history. What this same oscillation, this eastward surge of warm Pacific water, was capable of doing when it became extreme, and when other conditions lined up around it. But here the story has to slow down, because there is a dangerous misunderstanding to avoid. This is not a prediction that 1877 is about to happen again. The world that endured that catastrophe had no modern seasonal forecasting, no satellite view of expanding drought, no global food trade at the scale that exists today, and no comparable system of reserves or rapid distribution. In that century, when a monsoon failed, starvation could remain local and lethal because food could not be moved quickly enough. We do not inhabit that same world. The reason to return to 1877 is not to suggest another 50 million deaths. It is to understand the physical reach of the phenomenon itself. So when a top-tier event becomes more likely than not this year, the subject is not merely a wetter winter in one region or a strange season on a weather map. It is a planetary lever that, at its most severe, has helped redirect human history. And one part of the comparison is especially sobering, because it does not favor the present. The great satellite-era El Niños and the disaster of the 1800s all unfolded on a cooler Earth than the one beneath us now. The El Niño developing today is rising from the warmest baseline in the instrumental record, over an ocean that has been absorbing extra heat for decades as the atmosphere has changed. That means comparisons with 1997 or 2015 can quietly understate the risk in one particular way. If the peak appears similar, 2 degrees or 2.5 degrees of El Niño warming, it is being added to a higher starting point. The same measured strength now can place more absolute heat into the system than an equivalent event 40 years ago because it begins from a warmer floor. The oscillation may have a familiar name, but the platform beneath it has shifted. That is why careful scientists warn that even a peak number we recognize could bring outcomes we do not, because the event is loading onto a planet that has not started this warm before. In that sense, history is not a side path. It is the deepest evidence for the central point. Past records show the Pacific as one of the strongest natural controls on weather and harvests across the globe. The satellite-era giants reveal what the upper tier can do in a modern world. The 1800s catastrophe shows the ceiling, when the lever reaches an extreme and the surrounding conditions amplify it. And the warmer baseline tells us that the present event is forming on ground no earlier event occupied. So the rapid onset, discussed throughout this story, the way it moved ahead of the models, is more than an interesting forecasting problem. It may be the first visible edge of a top-tier capable event. Building ahead of schedule over the warmest ocean yet measured, with months remaining before its expected peak. History cannot tell us the exact shape of what comes next. It can only remind us of the scale of the force involved, and caution us not to feel safe simply because the label is familiar. To understand why 1877 became so devastating, we have to look not only at El Niño itself, but at the way it connected with the rest of the climate system. That event was not a Pacific anomaly acting in isolation. It coincided with other ocean anomalies, a warm Indian Ocean and a warm Atlantic. Together, those conditions meant that several major rain-bearing systems faltered at once. The monsoons that sustained much of Asia failed to arrive as needed. The rains that nourish Brazil also did not come. And because these failures were spread across continents in the same window, there was no easy surplus elsewhere to balance the shortage. Especially in an era without a fast grain-moving system capable of changing the outcome. Tens of millions died not because one drought, by itself, was beyond survival, but because too many food-producing regions were stressed together. That is the lesson that still matters. Modern researchers are not chiefly warning about the return of that specific death toll. The concern is synchronization. The chance that a strong El Niño can press on several major growing regions at the same time. In a food system that often behaves as though failures will occur separately, this is why the oscillation is watched so closely. Studies have shown it is among the few forces able to create globally synchronized crop stress, which is why a giant event draws the attention not only of meteorologists, but also of economists and grain traders. The satellite-era giants deserve to be remembered in human terms as well, because a graph showing 2.5 degrees does not convey what such years felt like on the ground. The 1997 and 1998 event forced hundreds of thousands of people from their homes through floods and landslides, contributed to disease outbreaks in disrupted regions, and helped feed vast wildfires in drought-stricken forests across the far side of the Pacific, with smoke severe enough to choke entire countries. The 2015 and 2016 event pushed tens of millions into food insecurity across Africa, Asia, and Central America, while also driving the worst global coral bleaching documented up to that time, killing reefs that had endured for centuries. These were not simply years of bad weather. They were humanitarian and ecological events on a global scale, recognized as such while they were happening, and they peaked below the level where the central forecast now points for the event taking shape. When forecasters say the current El Niño could rank with those events, or even exceed them, that is the category being invoked. Now keep returning to the one difference that makes every comparison less comforting: the warmer floor. All of the great past events happened on a cooler planet. The El Niño forming now is developing against the warmest baseline in the instrumental record, in oceans and an atmosphere already carrying decades of accumulated heat. That does not tell us the future with certainty, but it does change the meaning of every familiar benchmark. And it raises the quiet question at the center of the story. What happens when an old planetary rhythm plays out on a world that is no longer starting from the same place? Even if this El Niño reaches a peak that seems recognizable on paper, even if its final number falls near the territory of 1997 997, or 2015, it is not rising from the same world those events rose from. Its pulse is being added to a baseline warmer than any previous event has had beneath it. Heat waves that it strengthens are beginning from a hotter background. Droughts that it worsens are already starting from a drier place. The seas it pushes upward are already unusually warm. A familiar summit, placed on an unfamiliar foundation, does not lead to familiar outcomes. It points toward a climate response we have not yet experienced in quite this way. That is why cautious scientists are not comforted simply because older events offer comparison points. The number may echo the past, but the setting does not. And again, the feature they keep returning to is not only how high the event may climb, but how quickly it has begun to rise from this new floor. That brings us to the question that has been waiting beneath everything. We have measured the heat, traced the machinery, and seen the models fall short. We have watched the Gulf fill with water, the American summer gather force, Europe endure extreme heat, and earlier events return like shadows to show us scale. Yet all of this has been prologue. None of it is the crest. So before we leave, we should stand quietly at the edge of what is known, look toward the months still ahead, and ask the question scientists may be asking in careful language. If this is only the beginning, what might the ending look like? Let us try to approach that answer. Part 9. The question beneath the records. Return for a moment to the place where this story opened, that band of ocean along the equator that set a record for 5 straight days. The fact is the same, but it should feel different now. At first, those 5 days may have seemed like an odd streak in a remote part of the sea. Now, the background is visible. You know the advisory arrived early, weeks before the usual calendar would have suggested. You know this year's line has been running above every year since 1940. You know the Eastern Pacific tripled its anomaly in 5 weeks. You know the official index moved a full degree away from a cold starting point across 2 seasons. You know the forecast already points toward the top tier. And you know the most aggressive model in the world is considering a peak beyond every giant event in the record. In that light, those 5 days are no longer a curiosity. They are the first exposed rim of the largest natural climate event the Earth produces, arriving early and moving faster than the best tools expected. This is the central thread that has run through the entire story. The warmth matters, but the pace is the warning. A warm Pacific was not a surprise. This event had been coming into view for months, and a warm Pacific has a known playbook. What was less expected, and what the models undershot, was the speed of arrival and the force of the climb. In a system this vast, speed is not a footnote, it is a signal. It suggests that the forces now overlapping the record wind burst, the loaded ocean below, and the warmest baseline ever measured are pushing the system toward the edge of what can be forecast with confidence. So sit for a moment with the harder question, the one likely asked in the cautious, hedged language of scientists who do not want to exaggerate. If the opening stage has already outrun the model, what happens when the peak arrives? That peak is not expected until late autumn and winter, still months beyond everything we have examined here. Every record line, every comparison back to 1940, every surprised forecast belongs to the beginning, not the top. The Pacific has not yet shown its full height, and an event already moving beyond charts, already ahead of schedule, with the entire back half of the year still available to press on hurricane seasons, droughts, harvests, and winters, is not a story with a neat ending to offer tonight. It is still being written, quietly but relentlessly, in the temperature of the water. What can be said, somewhere between denial and doom, is this: the year ahead is likely to matter. The Pacific dial has been turned sharply, and its response may appear place by place and season by season, in storms over the southwest, hurricanes off Mexico, swells against California, floods across the southern tier this winter, and deadly heat that continues to appear from continent to continent. Some signals may seem counterintuitive, such as the Atlantic being partly restrained while the Pacific is energized. Others are already close at hand, like the flood watch over Texas tonight. None of this has to be accepted on belief alone. The same index used by forecasters can be watched by anyone. The same coastlines can be observed. The dial is public, and now its language is more legible. Before the difficult part, there is something practical to keep. Understanding becomes more useful when it gives you a way to follow the unfolding pattern. You do not need to wait for a headline to be told where this is going. You can follow the same numbers forecasters follow. Watch the official index, the 3-month average for the Central Pacific, and see whether it continues climbing toward and beyond the very strong line of 2 degrees through the autumn. Watch the Eastern Pacific off Mexico, and notice whether the next storms remain weak and subtropical, or whether they begin making the rapid jumps that warm water can allow. If you live along the southern tier of the United States, watch your own sky and see whether winter brings the procession of storms favored by a strong event pattern. Watch California for atmospheric rivers. Watch the Gulf, which is already revealing something this week. Each signal is another readout from the same dial. The value of understanding a system is that it changes the way fear behaves. Fear alone leaves you waiting in the dark. Understanding lets you watch what is coming with your eyes open. And while you watch, keep both sides of the honest picture together, because either one by itself can distort the view. The first side is that this is real, large, and already underway. The advisory has been issued, records are falling, the Gulf is flooding, Europe is baking, and the central forecast favors a top-tier event while there are still months left for it to build. Anyone insisting that this is nothing, that it is merely an ordinary summer, or that the records are just noise, is not reading the data the cautious institutions are reading. Yet the other side of this story matters just as much. The most severe possibilities are not guarantees. A projected peak is a measure of probability, not a sealed outcome. El Niño has caught observers off guard before, sometimes weakening when it seemed ready to intensify, and sometimes strengthening with unexpected force. The same uncertainty that allowed this early development to move ahead of the models can work either way. So when someone insists that disaster is already fixed, or that the worst scenario is the only scenario left, that certainty should be treated with caution. The more difficult truth sits between denial and alarm. The risk is significant, the danger is real, but the future is not fully written. That is why the steadier response may be to keep watching closely, without panic and without turning away, always keeping the error bars in sight. What lingers here is not a prediction, but a question still waiting for an answer. And in a quiet way, that may be the most important part. For as long as these observing tools and models have been available, there has been an assumption that events like this would give us warning, enough time to see the pattern forming and prepare. This year, in its opening phase, the event moved faster than the model pathway suggested. Perhaps that will prove to be a single miss, a strong wind burst, an unfortunate combination of conditions, something the next forecast will handle more cleanly. Or it could be hinting at something deeper, the possibility that the warning system we rely on is being challenged by a climate system moving faster on a planet that has never been this warm. No one can say yet which interpretation is right. That uncertainty, resting on the climate's most powerful lever while the peak remains months away, is both the most honest and the most uneasy place to pause. The Pacific is breaking records sooner than the models expected. The records are still being rewritten, and the season has not yet reached its end.